Good morning, Glasgow. Are you having fun? Yeah. Okay, I just came from the Fringe Festival. I had 7 days of comedy shows, so I can't talk in any other way. So, are we having fun? Yes. Okay, let's try something more puzzle. Are we all awake? Yes. Right, so this is a tutorial on Lean. Sebastian Ullrich and I will be giving it. It's going to be a lot of live coding by us. And this tutorial is for you, not for us. So we need to know who you are. So I'm going to do a little bit demographics check. Don't worry, you can raise your hand. It's not on comedy. I will not ask personal questions. Whoever raises their hand first. So let's see. Who has, let's start with the specific one. Who has worked with Lean before? And just doing a tutorial is good enough. Just who has opened it and done more than 2 lines of Lean. So we have like one, raise it all the way. Come on. 2 lines. Just like one exercise. Getting more. Yeah, okay. So 1, 2, 3, 4, 5, 6, 7, 8. Those of you who haven't, look around now and look at who have raised their hands, because if you do the exercises later, these are the people you may want to team up with. So this is, I mean, it's a tutorial, but really in 2 times 90 minutes, it's not really realistic to get somebody who has never seen an inductive theory prover before up to speed to Lean, where you can just do something interesting on your own. So we will have exercises. Some of them will be like the cargo culting level, where there's some existing code and you have to write similar code next to it. If you may be able to do that on your own, but it's more fun if you do that. Okay, let's cast the net a little bit wider. Who has worked with, okay, let's exclude the people who have just raised their hand. Let's do a little bit of set theory here. Okay. So who has not raised their hand, but has worked with other inductive theory provers before? Cork, Acta, Isabel. Okay, that's reaching already half the crowd in the union of these things. I'm curious. Let's do the different theory provers in a row. So who has worked with Isabel? It's half. Just raise hands. Who has worked with Acta? Okay, we're in Scotland, I can tell. And who has worked with Rock? And who has worked with Cork? Well, it depends on like when you started, you know. Like you can tell the people who have done it for more than 6 months from the people who have. Okay, so it looks like we actually have a fair number of people who have done inductive theory prover before. Just double check. Who has never used an inductive theory prover before? This should not be everybody else, I assume. Okay, that's still a fairly large group. So we have a diverse group. This will be interesting. Okay, this is more about the tools. Let's see about the theory. Who would claim that they have a rough idea about programming languages semantics? If I say what does it mean for small step semantics to be adequate with regard to big step semantics? Who is not completely lost? Okay, this is good, and it's also good to see that there were some hands up from people who are not used to theory provers, because this will be our example. We will be doing some very standard imperative language formalization together now with Lean. So even if you haven't seen a theory prover, you may recognize some of that. And if you haven't seen neither, well, there's more for you to learn than for all the others, which is also good. Okay, let's see who's eager. Who has, in preparation for this tutorial, installed Lean and/or cloned the repository that we uploaded? Which was much better than the last one. That's good.
That's a bit problematic because there will be multiple files.
Is there any Microsoft?
There is an Emacs extension, there's a new Vim extension. It might take a bit more effort to set that up.
Okay, so VS4 is the...
Yeah. You can also team up with someone who's installed it.
Okay, counter check. Who has not prepared? Just be honest, it's fine. Okay. So you can just look at the screen. As I said, it's a tutorial, but this is not going to be a hand-holding all the way so you can do everything on your own thing. So it is okay to just sit back and watch us do it and try to follow along. The more important thing is, as you do that, please ask questions. Please stop us and say, I didn't get that. You can also tell us, try something else. Why are you doing this? Is this really necessary? Isn't this much better in Lean, in Isabel, and then we can go off in tangent. We don't have to go through the theory we have. We very certainly won't go through all of it in detail. And I'd rather go slow and take all of you with me than rush through the program. So the more interactive we can do this, the better. Last time we did this, I had to something about Fibonacci numbers or something that I got to formalize randomly, kind of worked. So please take us where you want us to be in the context of this tutorial. And right, and if you look at the repository, there are some files. We're going to develop them together now live. And then there's some exercise break. We'll see if it coincides with the break, or if it just give you 10 minutes to play around with it. If you walk around, we'll improvise that. Anything else we need to get to know before we start?
I think that sounds good to me.
Okay, then clap your hands loudly for our first act of the evening, of the morning. Sebastian Ullrich with the introductory slides.
Okay, I maximize that. F11? Should I?
Space.
No, maximize.
Oh, you want to?
Yeah. Let's do this the professional way.
Oh. Not very professional.
Oh, this is great. Okay, perfect.
Good.
Yeah, so this is not the live coding part. We thought we should give you a little context about Lean before we get to that, because, well, yeah, we'll only be able to show you a very specific slice of Lean today, and so it might be interesting to hear about at least what people are using Lean out there. All right, and yeah, I'm really happy to have this this crowd with a real variety in the room. And so, for example, if you come from a more automated theorem proving or formal verification background, you might be interested to hear that how did Lean even get started. It started from the SMT world, because Leonardo de Mura, the creator of Lean, had created the C3 SMT server before that. And so he saw interactive theorem proving as a solution to scaling and control issues he saw in SMT solving. So yeah, that's how the project even started, why we have this theorem prover. But yeah, so all in all, it was created as an automation platform. But yeah, not like this black box automation that you have in SMT solving in other systems where you only have a push button, but white box that you can create your own automation with it. Yeah, and fundamentally, this is of course an interactive theorem prover. It is also a functional programming language. You can write very standard functional programs in Lean, and you can write functional meta programs in Lean to extend Lean using itself, as we will see later. And yeah, simply if you're curious about the name, why is it called that anyway? Yeah, this is a technical aside, we won't have to worry about that in the remainder today. But yeah, it is called Lean because the kernel, the trusted code base, is comparatively small to other systems that are based on type theory. And yeah, this is what Lean looks like, what we'll look at in a moment. You have AO editor, you have VS Code, you have the input on the left-hand side, for example, and the output of the prover. No goals, so we're done in this case on the right-hand side, but we get into much more detail on that in a second. Right, so when I talk about Lean, what does it mean anyway? So of course there's the Lean compiler, if you will, the executable that takes your code and tells you if it's correct or not. But of course there's also a build system around that. There is of course a plugin for editors. VS Code is the one that we are developing ourselves. There is a by now very big standard library with all the most relevant data structures in it. We have search search systems. We have a manual, of course, and that is in fact written in a documentation system implemented in Lean, so that you have a documentation language embedded in Lean. Just as another example of the extensibility of Lean. Right. So yeah, what are people using all of this? Well, certainly what they got started with, the first big projects around Lean, that was in mathematics. So the liquid tensor experiment that was in 2021 was one major project where the fields medalist Peter Scholze had a proof. He was unsure about that. He didn't quite comprehend his own proof. He couldn't say if that's all correct. And so he asked the Lean community to verify that for him, and they did. They simplified it even, and they did all that without understanding the whole proof, because all they had to do is to teach Lean how to get from one step to the next step, that is correct, and then Lean could verify that the entire chain is correct. And when you do a project in this chain manner, then that also means you can have suddenly have a lot more contributors than you usually do for a mathematics paper. Right, but if you're already familiar with ITPs, I'm probably not telling you too much new on this slide. So let's go forward. More relevant maybe for this crowd is software verification. There are also first projects being done in that. So already from last year, Sensor was a very nice one that also combined the mathematical library for differential privacy verification. There's also a very nice PLDI talk about that if you're interested in it. And just to focus on one example, this is a new slide I added this morning because it was such a fitting example. There's not just singular projects being done in Lean, but entire verification frameworks. So this is the Whale framework by the group of Ilya Sergey at NUS. And this is for verifying transition systems. And then you have code for transition systems, like on the left-hand side, that almost looks nothing like Lean to me anymore. But it is a embedded language into Lean to benefit from the upsides of verification in Lean. So you can write down your transition system in Lean. On the right-hand side, you can state some invariants that I don't want to share too much about. And in the end, you can say, well, please check my invariants, and it will generate an automatic proof. But everything will go through the Lean kernel and be checked. You have the same guarantees as with a manual proof, which you can still do. So another example of white box automation, if you will. All right, and so this specific example, let's take a language that's nothing like Lean, but let's embed it so we can reason about it in Lean. That's in the direction you want to go today. Right. One last topic that people are also interested in about Lean, that is AI. More recent topic, and so we had last year Google DeepMind using Lean to get a silver medal. They set a silver medal level at the International Math Olympics. That was completely unexpected. No one thought LLMs were already at this level of formal reasoning together with Lean, but they did it, and so they output a proof on the right-hand side about one example of the IMO problems, and Lean verifies that proof, and that is how they claimed this silver medal. Right. One last information slide. Who are we anyway? yeah, so well, maybe you saw lead throw on the first page. What does this firm mean anyway? That's a focused research organization. So we're not directly affiliated with a university or a for-profit company. We are a non-profit that's dedicated to the development of lean. And so, yeah, maybe the most interesting part on this slide for you might be, depending on what you want to do, for example, after your PhD, is that there are career paths between academia and industry as well. And I do hope that this will be even more prominent in the coming years. Right, but without further ado, I would say let's get started. So yes, we want to verify some foreign programs in Lean today, which means we want to embed their language in Lean. We've already mentioned we want to give those some semantics. We want to prove something about them, of course, both about specific programs and about optimizations of arbitrary programs. And yeah, then we'll see if we can give some more pointers as well. Right, and so you might already know the language that we want to embed today, because it's a very common example language. It's like, what's the simplest imperative language you can think of? So yeah, it's ordinarily called imp. We have while loops, we have conditionals, if statements, we have assignments, and that's all we need to write some simple programs, right? Yeah, so we do have mutable variables, of course. It's imperative, but yeah, we basically have only global variables. We're not worry about local variables in scoping today. And yeah, we'll say 32 bits, that should be enough for everybody, right? Right, so yeah, some very simple examples. I hope that this syntax does not look too foreign to you. Great, and I think with that we can get started. Any questions up to this point? Yeah. All right, let's get started. Can you tell me the caps free? All right, that worked. Great. Okay, so this is VS Code. On the left-hand side, you can see my screen. Should I make my text editor? Should I make it a bit bigger? Maybe more like this. Yep. This is good. Right. So how do we get started? Yeah, we want to embed this language that you just saw, and we want to start small. We want to start with the expression language, the arithmetic expressions, logical expressions in this language. So how do we do that? If I write something like, we want to have an inductive type called expr in that describes our arithmetic language, then who's still with me? Who's saying, well, inductive type or algebraic data type, I'm familiar with that. Okay, so if you're not immediately familiar with that, yeah, you should really think of this as our abstract syntax tree. So let's say we have a non-terminal expr. What's all the ways we can create terms of this non-terminal? And well, what's the simplest thing we can think about? Well, what about, well, we just have a number. Let's call that a constant. And yeah, we said we have 32 bits, so let's do that. So any I that is of u int 32, unsigned 32 bits, that's a valid expression. Okay, makes sense so far? Yeah, what else? What simple thing do we have? Well, we need variables, right? We want to refer to variables in expressions. So let's say we have a var constructor, and well, that takes a name, a variable name, and we'll just make that a string today. So that's something, yeah, that's how we can refer to variables in this expression syntax. Right. And so maybe at this point it's nice to play a little bit with this. And one way we can do this in Lean is to use the check command, which you can give any term, and then Lean will say what he thinks about that term. So we could say something like, oh, check that expr.const is a valid Lean term. And yes, then Lean, well, it doesn't complain, so that's a valid term, great. And it also tells us on the right-hand side, which is where the output of Lean is happening, well, it's an expr. Yeah, okay, not too surprising. And then, of course, we can go further and say, well, expr.var with the string x, that is now a valid expression as well, which is referring to the variable x. Right, but of course that's still a bit of a boring language. We need a way to actually combine terms into larger terms, right? And so, well, we probably want to have something like a plus operator, right? And so how do we do that? Well, what does plus do? It takes two expressions, let's call them E1 and E2, and it combines them. Right, and so let's try that as well. Let's just try to add together exactly the two terms we already had. Okay, and we get a new expression. So this is the expression referring to 0 plus x. Right, and now we could continue with this, with all the other operators. It gets a bit, yeah, it might be nicer to categorize this a bit and say, well, we have different binary operators, but they all have the same shape. So let's just say, well, what are all the operators we're interested in? It's like plus, minus, times, diff, maybe a few others, but let's just stay with this for now. And now we can say, well, any operator that's such a binary operator can be used to combine two expressions. And now we'll just adjust this one as well. And we still have a valid expression. Okay, so that's the very basics of how our expression language can work. And I'm already getting a bit tired of this. Like, this is no way to write down a program, especially a big program that we want to prove something about, right? So, well, one first thing we could do is let's use a bit of syntax sugar and say, well, we have to repeat expert all the time because that's just the name of the constructor. But in fact, in this position, Lean already knows that an expert is expected here. It even tells you that on the top right-hand side. So we can actually just use a little syntax sugar and say, well, use the const constructor of the type that's expected at this point. So we can abbreviate this a bit, but it's still not very nice, right? And we want to get to a nice level of Rail that we saw, where we really can embed a program effortlessly, that it still looks like it would look in literature or wherever we are taking that program from. All right. Anything else I should be mentioning at this point? Well, we can still clean this up before we get to the next step. I mean, we created a type expr now, but maybe someone else wants to create a type expr as well, right? That's not a very specific name. So just a nice thing to do in general is to maybe put all of this into a namespace, and we call that imp, like the name of our language. And now, if we control space. No, I don't think so. Control dot. No. Okay. If in the standard configuration, if I had a hover here, I would see that all the types, all the names are now prefixed with imp. So now our type is actually called imp.expert, and there's imp.expert.const, but within the namespace we don't have to worry about that. Okay.
Control I.
Works? Great. Yeah, imp.expert.const. All right. Great. Okay, what else can we do here? So one nice thing is that this check is convenient for quick prototyping in the editor, but we can even use it as a bit of a quick unit testing framework, because we can say, well, we always want to make sure that expert.const0 remains a valid expression. How can we make sure of that? Yeah, one very simple way to do that is to use the guard messages command, which simply says, and then I can use a code action. No, why does it? Yeah, here it is. To say, yeah, I want this command to always output the string that you see above. So we could basically commit this as a very simple test to our repo now to make sure this output does not change. All right. Okay, but let's now focus on our first goal. Let's give this a nicer syntax. I don't want to look at those constructors anymore. That's not a way I can write any larger program with. Right, so let's talk about embedded syntax. Yes?
So is the guard message, I just want to know, the guard message only checks the output from the interpreter?
Yeah, you can
just
use
a string, just a raw string from the interpreter.
Yes.
So I'm not sure whether it's a very stable feature, but what if the compiler got updated and the message has been, the format of the message has been changing, and suddenly all the guard message that previously typed are no longer valid.
That in theory that could happen.
Uh-huh.
At this level, I would not expect that output to change, because there's not that much different ways we could even format the specific output, and it is I can't think of a previous change that broke that.
Right.
But yeah, I mean you're definitely right that in that this is a very low level way of testing. You could use very other high level ways to have a more robust test. And yeah, I would say this is most useful when you're testing your own output, because then of course you have control over it.
And maybe one point out that with guard messages, you can compose with any kind of lean command that has an output. So it's not just check, you can put guard message on things that put error messages, you can even test whether things fail in the way you want, because it's just asserting that the next command in the lean has a certain output. So it's very flexible.
Just want to ask further, does it support regular expression?
No, but you can write a guard message variant yourself rather easily that does it.
Okay.
So it's not baked in, it's
Okay.
part of a very extensible lean setup already.
What are the little squiggly on the left?
Yeah,
Or
that's
the first one when you added guard messages or something.
yes, so that is simply output on the right-hand side. That's also repeated on the left-hand side. So if you hover over it, you can see the same output. Yes, so the guard messages takes that output and puts it into that comment. So that's why it vanished from the editor itself. But yeah, that's basically, I would say, implementation type detail of guard messages.
This is your basic one. Is a line 15 a valid syntax?
Yes.
Okay, so basically I have to like prefix the data constructors with a dot.
Yeah. You can do that anytime Bean already knows the type of that constructor.
Okay, so otherwise I have to like prefix it with the type name.
Yes, exactly. And so I should really show this. I can't remove that for the first expert because, well, check doesn't know what type we want to check. So if I do that, then it says, well, I have no idea what type this is. So I need to, oops, that was a bit much. I need to keep this expr dot this single expr here, and then I can abbreviate all the others.
So basically, you have to like when you start with some type and then.
Yeah, yeah. You have to tell Lean once what word you code in, and then it can infer. Well, it can usually infer the rest. All right. Time to get to some syntax. Right. So how can we make this prettier? Right. And we'll start any of these syntax adventures usually by declaring a new syntactic category, which we'll call exp for our expressions. And so what does that do? It means that, well, you should really think of this one as a non-terminal, but now we're talking about concrete syntax. And we can fill that with syntax using the syntax keyword. So, okay, so if we want to think of a nice syntax for our term language, what can we do? Well, first of all, if we just have a number, a numeric literal, that should be a valid expression in our syntax, right? And let's try to immediately test that. Well, I can write check1, and that is a valid Lean input, but of course that's just the built-in Lean semantics of the number 1. And now you see on the right-hand side, the 1 is a natural number. Okay, but like that's not surprising, but that's not what we wanted. We want to embed our own language. So what we're really missing to make this work is a way to combine our new syntax with the syntax that already exists in Lean. And yeah, usually how you do this is you give a syntax that lets you embed your new syntax in the old syntax. So we could say something, well, whenever we have syntax in the X category, we also now have syntax in the term category. And this is the category that's already built into Lean. You can see there's a hover, which tells us term is the built-in syntax category for terms. So that's the category, that's basically the parser that is used after the hash check. And now we can do something like, yeah, let's use our new syntax. That's X followed by braces and then a term. And this is now being parsed. So the parser already accepts this, but we still get an error. So what does that say? Elaboration function for something has not been implemented. Okay, that means we've created some new syntax, but we haven't given it any meaning, right? Lean does not know what to do with this syntax. Right, so next step is to give it meaning, and we'll do that today using the macro system in Lean, which means that we'll simply take our new syntax and translate it to syntax that already exists. That's a very simple way to give meaning to a new syntax, right? That's basically syntax sugar. All right, so how do we do this? So in parentheses with this backtick, that's a syntax quotation. That's how we can refer to and match on syntax. And so we can say, well, whenever we use our new syntax exp with the braces and then an embedded expression, we want to translate that to something new. Right. Okay, so what's happening here? We have the dollar, which just means there's a hole in here. We want to capture the syntax that's at the position of the dollar. And now Lean actually tells us what we have to do. We get E is a syntax tree in our new syntactic category, and we want to translate that to some other syntax tree. That's what the macro does. And yeah, you can in fact write arbitrary Lean programs on the right-hand side here to translate that to new syntax. All right. But so how do we do that for any E? Well, let's start small. I mean, what if we want to translate a numeric literate, like exactly the test case we already have below? How can we give that meaning? Well, we've already seen that Lean knows how to check 1, so and we want to embed that into our const constructor, and then we can simply say, well, take the n and put it as an argument to the const constructor. All right, now something is happening, and this is being accepted, and if we look at the right-hand side, we see that, in fact, our new syntax tags exp of 1 is being translated to expert.const of 1. Okay, does that make sense so far? So this is a simple syntactic translation.
There's a question over there.
Yes.
Is the backtick some sort of macro situation, like, quote unquote?
Yes,
Okay.
yes, this is a quasi-quotation. The backtick starts the quotation, and the dollar is the anti-quotation.
Okay.
Okay, so let's add some more syntax to that, I would say, because so far our language is still a bit boring. Right, and so I would say, well, let's add some variables as well, right? And we don't want to refer to variables as string anymore. What we actually want to say, well, we can just write down an arbitrary identifier, and then that's a valid exp. Okay, let's try that. Well, it's accepted by the parser again, but again, needless know how to make sense of that new syntax. We haven't given it any macro root or anything else. All right, so let's try that. You're saying, okay, if you see any ident inside these braces, then translate that to, well, not expert.const anymore, but expert.var. And, well, let's give it a first try. We could say, well, yeah, just put the ident in the argument position, and then that doesn't quite work, because now Lean says unknown identifier x, which makes sense, right? There is no x in the scope in the Lean sense, and we're simply saying, well, take this x and put it as a Lean identifier x. And so that doesn't work. We actually want to create the string that we saw before. And so this is the point where we get into basically writing arbitrary programs on the right-hand side. But you shouldn't have to worry too much about this part. That's you don't have to get into the details of that. So what we actually want to do with this identifier is get the actual name of this identifier, and then we'll turn that into a string, and then we'll have to turn that string into the syntax of a string, and then it turns out it works. Okay, so yeah, that's a very small outlook into the depths of macro programming. Let's not worry about that part going further. But what you see is that it works. We have now transformed the input of x into a string of x inside our var constructor. All right. What else is there to do? What about our binary operators, right? So we want to say something well, like x plus x is syntax for an expression, right? That would be a very natural way to input this. Well, let's see if we can do that. And actually, I think, yeah, doesn't matter. Okay, so we want to input something like exp of x plus 1 now. And yeah, again, this is now valid syntax. It doesn't have any meaning yet. All right, let's try to give it some meaning. So, okay, so what do we do now? Well, let's just follow the syntax. Let's match it and say E1 plus E2. We want to give that meaning. And now we see on the right hand side we have access to these two syntax trees and want to create a new syntax tree. Okay, so what does that look like? And then just insert a line break here, that's not too long. So how do we do that? Well, certainly we want to use our expert.out constructor, right? And we want to do it with plus. And now we have to do something for the arguments. But E1 and E2 are still in the are still AXPs. They are not lean terms. So what we want to do is to just recursively use our own macro and translate those two lean expressions first. And when we do that, it should turn out that, in fact, this works now. Right. Okay, so this is already a much nicer way to write down this verbose construct on the right-hand side, right? I mean, we had to do a bit of work, but yeah, I think what we want to show you today is if you put in that work in the upper half, then you can create a very nice compact syntax in the end, and yeah, even scale that to projects like Whale, where you really embed your domain-specific language and not just a very simple expert language. That's all we can get to today. All right. What else should we do? Well, let's add one more operator here, right? And then we can talk about a new issue, which is, let's do times. And let's try that as well. X times 2 does not work because I think I did not actually call it times. Is that correct? Oh yeah, I typoed that. And now it works. Okay, okay. But that's not the interesting case. That's just the same as plus. So what might be more interesting is to say, well, what happens if we now say x plus 1 times 2? And this is actually fine. Should turn it around. X times 2 plus 1. And now we see something unexpected maybe happening. Well, hopefully unexpected, which is that, well, it's hard to actually even parse the output on the right-hand side, right? Because it's so verbose. But you see that the times is on the outside. So what we are actually writing down here, according to our semantics and syntax, is the same as this one. And in fact, we don't even have parentheses yet. Should we add those quickly as well? I think parentheses could be good to have. So we can write this down just like we would in some BNF. And how do we give meaning to parentheses? Well, if we see an expression that's parenthesized, I mean, at this point where we simply have the expression and nothing else, we can just throw away the parentheses. That's how you give semantics to parentheses. And yeah, now we get the expected output here. We just don't get the expected output here, which we would expect to be interpreted like this, right? Yeah, and now we see if I do it like that, if I'm explicit, then the plus in fact is on the outside. Right, how can we fix that? And the solution is that we have to give our operators some precedences. And yeah, without going too much into that, what we really want to say is that, well, you can't write a plus on the left or right-hand side of times without parentheses, right? And so what we usually do here is we give the plus some precedence, 65, let's say, and then we can say the times, well, you can only accept an operator that has precedence at least 70 on your left and right hand side. And as soon as we do that, it should change the way this is parsed, and in fact the plus is now on the outside, on the outer side, because we told the times do not accept the plus on your right hand side or left hand side.
Why don't you undo the change, use that message, and show how this would work in like a.
Oh,
in a real-
okay. Yeah. Let's try that. Okay, let's undo that. Let's commit basically the wrong output. Now let's redo the fix. And it's broken. It says docstring does not match generated message. Because, we committed that there should be a times on the outside, but now there's a plus on the outside. And if we say now, well, the new output's actually correct, we want to update that, we trigger the code action and say update output. And now we have committed that new behavior. Right. Yeah.
So just to be clear, so we have like the ASD with the
Yes.
expression like with capital E,
Yes.
and you are defining a concrete syntax called next, and you are writing a parser to like that translate to like the ASD. Okay, so and we are doing everything within it. So the word num, I didn't, that has no meaning, right? You have that just arbitrary choice,
Yes, I can actually, let's see if that has a hover. It does not. Oh, I'm surprised by that. But yeah, so when I said let's accept any numeric literal s and exp, that's something that's already a parser basically that's already built into
Oh.
it. That's the same parser that's parsing the one outside of our language.
Okay.
So we can just simply reuse that existing parser.
Okay.
Could you scroll to the right for line number 28?
Which one?
Line 28.
28. Oh yeah. Oh yeah, this one.
Yeah, just scroll.
Yes. But you're trying to replicate that. Yeah, great. Otherwise, I would say don't worry about this line. But yeah. All right. I think there's one more thing you need to do, which is how can we, well, we can create very specific programs here, but how can we create programs that generalize over other programs? And well, we've already, there was already the question about lean quotations and anti-quotations. And so what we really want is a way to embed lean terms into our quotation, into our expression language. And we'll just use the tilde for that, just as in usage. And I quickly demo that. And well, what happens if you use an anti-quotation in a quotation? They just cancel out each other. And if I do that, then we should now be able to say something like, well, for any n, what's the, for any sub-expression, what's the exp of e plus 1? Right, and I think at this point, I'm afraid to say I really don't feel so good today, so I think I'll have to give that to you. And oof, well, I really don't feel good. So that hasn't happened to me before.
No worries.
Oof, that's new. Yeah, maybe. Yeah, thank you. Let me just grab that. Wow, that's a new one.
Yeah, maybe take off your microphone. Go back first.
Okay. this was not part of the show, but I'm sure he'll be alright. So we'll carry on. Just means that I'm not have to tune in to see what other steps Sebastian wanted to do before I actually take over, which is, I think is roughly at the moment.
Sorry, I don't think your mic's on.
My mic is not on. I think it. Oh. Okay, test this. I think it's.
This is gonna be comprehensible.
I can take this.
Yeah, maybe the
No, it's on. Okay, no, it's on. Somebody did something. All right. Experiencing technical and human issues.
maybe further up.
Further up? I think this is fine. This should be good. Okay. Let me just quickly tune in. So I think we actually Sebastian heroically reached the point where he's basically finished talking about everything related to syntax. Almost everything. So just to recap, we have defined our data type for embedding our little language into like a deep embedding of the language into Lean, and because using the constructors is ugly, we defined our own little syntax within the meta language of Lean, and this allows us now to write concrete and even open expressions of type expert using the nice syntax. Sorry for that. Okay. But so far the language is kind of dead, in the sense that, okay, we have a data type, we can describe the language, but language is more than just syntax. We need semantics. Like we need a way to do something interesting with this language. So what I will do now is I will take everything that Sebastian did and revert it to the state that we had in the repository before. No, this was the wrong key combination. And I will start giving semantics. So the semantics for an expression language usually just means evaluating it. So the goal is we have some data, some value of this data type expr, and we want to turn it into a plain value. So I am importing the file we just wrote. It's actually the what is happening? Oh no, it's already. Is it one of these things where I can't talk into one direction? Okay, we'll see. Actually, let's also import the nice syntax that Sebastian wrote. And let's import our file we want to talk about. Okay, I'll talk about it briefly. The syntax file that Sebastian wrote, basically in the repository it's a separate file, which is why it's here. This is what Sebastian wrote with a bit more operations than just addition and so on. There's also a file called dlab, and if you want to look into the details of the file, is a bit stuff that you usually wouldn't do, but it's kind of nice in the sense that this tells Lean not only to parse the nice syntax that you have, but even produce it in the output. So if you look, so remember that when Sebastian finished and he was using the check command to parse one of these expressions, you would see the constructors here on the right. And this was hard to understand often. So the delaboration, which is the opposite direction of elaboration, is what Lean is using to print something to you. And here we teach it how to use our nice syntax, even when showing XML. But this is advanced magic. This is something I wouldn't know how to do it off the shelf. So we just put it in to make it nice. You wouldn't be doing that in your own projects, initially at least. And all right, so slowly getting back on track. Let's evaluate expressions. So the next few minutes are functional programming. So if you've been thrown off by all the theorem proving stuff, but you like functional programming, we're back on track. Let's write an interpreter for our expressions. And so we want to have either function that takes an expression and returns a value. Let's just give a name to values. So values, that's just our uint32. And now we can define a function. To define a function, we can basically write a lambda. Lambda is called fun here. So we take the e, sorry, what's happening? Okay, so we take the expression and we pattern match on it. Very straightforward functional programming. If it's a constant I, then we know the value. It is, okay, I need to get people awake more. The value is I. What is the value of the variable x? I'm trying to get this a bit more interactive now, so we'll... Okay, there are two comments. There's a question about the environment. What is the comment there?
The value is either x or whatever value is stored inside x, depending on how much.
Right. Now, storing things inside things, that sounds like very imperative programming. And as you see from my t-shirt, mutable state is a can of worms. So I'll go with this way. We'll have to add an environment. Environment is just telling the evaluation function about the evaluation of all the variables. And just to show a bit more syntax of Lean, I will put the environment into its own data structure. I mean, it could just be a function from string to value, but let's give this a name, and let's make a record type called env that has a field called get, and that will basically wrap the function that we expect. So it's a string to value function. And we can pass this environment down here. Sorry. I will use nice Greek letters because that's common in languages that are younger than 10 years, because now we have Unicode everywhere. So let's call it Sigma. I don't know why it's Sigma. Somebody who wrote this initially thought Sigma is a good name for environment. Say again?
Sigma for state.
For state, yeah. Which is strange for environment. Like other people might want to prefer capital gamma, but all right. So now we can use the env.get function on our environment to get the value of x. That's great. By the way, since we like these kind of syntactic sugary things, we already saw like the dot notation before, where if you start a name with dot, then it'll take the expected type to figure out which namespace to look for. We can do something similar here and say, I can use get as a method of Sigma. And we will see this a few times now. This is very superficial syntax, sugar in a way, in the sense that if Lean sees something where you use dot notation, like a method notation, it will look at the thing on the left, infer its type, take the first bit of the type, in this case env, and then just look for anything in the environment called env.get. It doesn't have to be a field, like a proper field, it could just be a function you define. And we'll see that in a moment. But this makes nice syntax without like heavy machinery like row types or something like that. Right, then the other case, we have operations like plus, and then two expressions. And now we want to evaluate E1. Actually, let me make it clearer by writing it out explicitly first. So eval E1, no, sorry. We have to pass the sigma down, E1, and then this is now a value, and we can add these normally. Okay, it's still complaining because we have missing cases. We actually added more operations there. I will just silence this while testing this by saying this is always 0. we can, let's test this. So far we've seen the check command, which takes a lean expression and gives you the type of it. So we can, for example, say that, oh, what is, if I take the expression of x plus 10 and evaluate it. Nope. I want this to be expert eval. Yeah. Well, for checking, I don't need environment. Checking just gives me type check, and it tells me this thing has type nth to value. But okay, let's give it an environment. We need, I guess we need an empty environment. So this is an env where the get function for anything just returns. Let's give it an initial value that we use everywhere. Okay, and now I can say env.init, I don't know, 2015. And this expression now has type value. But what we really care about is evaluating it. We want to see the value. So there's another command called eval, which takes the expression and basically compiles it and runs it. Or runs it through an interpreter. And this now means we can start evaluating our expressions.
I have a question. Why do you have to call it XPR is a type, right? So why do you have to define the evaluation function as x.eval?
So the full name of this function is imp.expert.eval. So names in Lean are namespace, dot separated things. And this is completely orthogonal from the module system or the type system. So I can just say everything in this file is in the namespace imp, but I don't have to mention it because it knows that I'm referring to things it's looking up in its current namespace. And I can now say this definition here in the namespace imp has name imp.expert.eval.
Okay, so I can think of namespace as different from types,
Yes.
So the EXPR on the left is different from the ESPR on the right. I mean, in the
right. So this is the right way of thinking about it. The namespace is very simple and separate from everything, and then there are these little convenience things where what I'm doing here, the dot notation, as I explained before, what it's doing is it's looking at the type of the left thing. The type of this experiment is going to be imp.expert, and then it's taking the name of the type as a namespace prefix and sees if there's an eval function there. And this means by giving the thing a name expert.eval, I'm now enabling the use of this nice dot notation to access it. This is not very deep. This is what makes Lean an amazing language, but in practice it's just so nice. I think these little things make, I've done Haskell before. Haskell doesn't have this, and now it has overloaded dot notation with fancy type classes. This is just so much simpler and more predictable in a way. Less powerful maybe also. Okay, well, we have more operations. Let's do the same ones that Sebastian also introduced. So we have plus times, minus, and division. Okay, there's repetition here. We don't like repetition when you do functional programming. So let's abstract out this common pattern of applying a binary operator to a value. And let's call, let me peek. Just to get the names right so that it matches what we do later. Right. So I'm doing the same thing again where we have this binop type, and I'm just defining a function called binop.apply that happens to have a type as a namespace prefix, so we can use the dot notation. It takes the binary operations and two values and returns a value. So we take the operand, E1, E2, and we match on E. And if it's plus, then we do E1 plus 2. sorry, if, oh yes. Okay, this gets repetitive, so let me see if I can enable Copilot and see if it helps me here. Yes, this looks good, this looks good, looks good. Does it know that there's more? Yeah, sure, whatever. We can do that. Does it stop? Okay. This looks like a complete match, so that was helpful. Thanks, Copilot. I'll just label it, otherwise I'll get confused a lot.
So when it like, you define all operations, right?
No, sorry, maybe I should have shown this. After I reverted the file to the one in the repository, and there we have more operations. We'll need these other ones just to show off at the very end. At the very end, there's going to be the cliffhanger why we have these extra ones. But yeah, we put them in here. There's also binary like Boolean operations, and and or, for example, that may be useful for some of the exercises. All right. With this in place, we can. Yes.
Why isn't it complaining that it might be undefined? Because if you have division by zero.
Oh, you're peeking ahead like this. I want you to ask this question in 3 minutes, maybe.
Okay.
Yeah, so, okay, actually, we're almost getting, yeah, I was getting to that point. So let's now use the operation here. We can now use O.apply. Remember that O is the binary operation. We can use dot notation, and then we apply it to the evaluations of the two arguments. And we can play around with this. So 2015 minus 10, that's fine, and so on. But yeah, one thing that you might find strange: what happens if I put in what happens if I now delete the 1 and we'll divide by 0? Let's see. Oh, it crashed. No, it didn't. Just keeping you awake desperately in the first session in the morning. No, it doesn't crash, but it gives us 0 as a result. Who finds this strange? Okay, a few hands. Who thinks this is absolutely the right thing to do? Nobody. I would expect at least those people who are using like Rock and Isabel are happy with that. Okay, so the reason why, and this is not specific to our own system here. We can just say 10 divided by 0 as like normal natural numbers. In lean, it'll say 0. It does similar things, by the way, for minus. So if we have 10 minus 20, that's also 0, at least for natural numbers. This is an endless debate, and you can go on Stack Exchange and find lots of discussions. I will briefly summarize why this is the case. This is also the case in other systems like Isabel and Rock, and probably Acta, I'm not sure. I mean, these are theorem proofs. They give you a logic, and this logic is like mathematically motivated and things. And if you have a function type from like net, like 2 nets to net, then this has to have mathematical meaning as a function on these sets. So you can't have partial functions as a value of the type of normal functions. So if you want to have minus as a function, it has to have some value. There's no place for like I'm aborting inside a sound logical system, at least not easily. And then it turns out that if you have to give a value, make it a nice value. Like you could define the whole logic of lean with 10 divided by 0 being 42, and it would be no worse than what we have right now. But if you make it a nice value like 0, then at least some theorems will be true without extra side conditions that you're not dividing by 0. So it's actually common to have this thing in the logic of lean or of a theorem prover. But here we're giving semantics to our own language, and maybe we don't want that our expression language has division by 0 as 0. So, but we are defining the semantics for our language, so we can fix that. So one way of, sorry, question. Yeah, please. What about defining like an option type or something? Good job. That's what we will be doing. We will be saying that the result of evaluating an expression, like if you want it to not divide by 0, then that means there are expressions that don't have a value. So we can't expect to write a function of type x per 2 value. So we'll say, okay, it returns maybe a value, option value. So option, that's, I can control click on it, by the way. This just goes to the definition somewhere in the library. This is what you know as maybe from Haskell, or option from anywhere else. Rock, Ocamo, all of them, Isabel, they have option. So it's either this some value, one constructor, or it's no value. And this is a way of modeling partiality. So now our evaluation function is partial. Now we can, like nice functional type function programming, we change the type, we get to fix all the errors until we are done. So obviously the apply function for binary operation expects a value, but this eval function returns an option value. The error message tells me this has option value, but we expect value. That's actually a helpful error message. This is always surprising. But we're getting better, and no worse than other systems. Okay, let's, quick hands up, who has seen do notation and the option monad before? Okay, half of you. I'll do it quickly. Going there. So, okay, if we can't apply the operator unless we have two values, one value from each side. So we have to. One thing we can do is we can match on eval on the first value. If it's none, then okay, the whole thing is undefined. But if you have a value on the first side, then we can look at the other side, the second argument, and there again, if we have a value, we can continue. And now this gives us the semantics that we want. No, not quite. It's still, the result is now an option, like it's type correct now. We get a result, but it's still 0. Of course, you have to. Yeah. I go. Question first.
Why you are not prefixing the constructors of option with dot now, like none.
If you look at the good point, this would be the standard way of doing it, kind of, because this now means the none option.none in the namespace. If you look at the definition of option, we will see that just below it exports the constructors from the namespace. So I can access them without namespace just because they're so common. But very well spotted. This is good. All right. We now have to, of course, change the semantics of binary operation application that it's undefined if we are in the case we don't want to. So let me I should have done that before.
So again, one more question.
Yes.
Yeah. So if we could do that, like, why would we have to like begin with dot in the first place? Like, we could, I mean, like in Rock, we could just do it like without dot, like. Just like dot is like a redundant thing.
I think it just makes name resolution more uniform. Like there's no special name resolution in patterns. Yeah. Okay, so let's change this so that if the second argument, okay, I think I want to, yeah, I shouldn't have written all these now because now I have to change them. Let's just, just to make this fast. Okay, I'm now matching on the values as well, so that in the case of division, I can have a separate case where if E2 is 0, then I'm returning none. Of course, I have to change the type of apply so that it returns none. And I have to have two patterns here. So this is a multi-pattern, like a match statement with matching on three things at the same time. That's possible. This is an overlapping pattern, so it looks from top to bottom. If it finds the case that we have division and the second argument is 0, we go to this branch. Otherwise, it keeps searching for the next branch, just as in most functional languages. And by the way, this pattern of like getting function arguments into scope and matching them immediately is so common that we can actually omit this part and just write this as a function by pattern matching guards. Okay, this should have fixed our function call down here. Yes, now this is none. Let's just check that the other ones still work. The other ones still work, that's good. One thing you may have noticed if you're trying to find out where I'm hiding things from you is that we changed the type from value to option value, but I didn't have to change some of these lines, right? So this is something that Lean has, it's called coercions. If it, put very simply, if it finds that two types don't match, like here we have something of type value, we expect something of type option value, then it uses the type class machinery to see if there exists a coercion from the one type to the other, and just inserts it silently. So here, Lean is inserting the sum constructor implicitly. There's actually debate if it's a good design that option has this, so maybe in a year it won't be the case for option, but there are other cases where you really benefit a lot from having these kind of implicit coercions. You're brewing a question?
No, I was just thinking.
Okay, well, keep thinking, thinking's good. All right, let me undo these changes, so, oh, that's fine. Okay, back to this code. This code works, like we match on the left-hand side, we get an option out, we check if it's none or some, if it's some, we continue on the right, and so on. This works, but it's ugly and repetitive. So now for those who have not heard option monad before, I'll briefly go there. So it's function programming. If you see a pattern, we can put in a auxiliary function, and this pattern here of looking at an optional value and returning none if it's none, and returning something else if it's some, that's called the bind operator of option. So there's a function called option bind, takes the option value, and then we also have to say what it should do in the case of if it's a sum value. So this, if you look at the definition of option bind, it's precisely the match that I just removed. And of course I can use it again on the second. So this is now already much more prettier. I can use dot notation here again, because this expression has type option, so I can option bind. This looks almost nice. And okay, let's go all the way. This is a binary operation that is just overload. Okay, let's skip the overloading. This is a syntax for the bind operator. And you may have seen it, it's not on my t-shirt today, but I sometimes run around with t-shirts with that symbol because I have a Haskell background, and Haskell has established these operators back then, and same as for them. So this is much prettier than the match statement, but we can make it even more prettier by using what's called the do notation, which looks like an imperative program, but it's really just syntactic sugar for exactly that, nested binds. So I say I want to do notation. I want to say I1 is the result of this call, and I2 is the result of that call, and then I continue with this thing. And this looks almost like an imperative program, but it's really just syntactic sugar for these option bind things. And then you can do this for many other things than option, and you have a really amazing way of expressing complex programs. Okay, I got sidetracked, but it was maybe interesting for those who did not raise their hand when they asked about the option model. Okay, I think I'm happy with the evaluation function. Besides the fact that, the other operations, I'll just revert this to get all the operations in place here. Doc strings. We don't need doc strings. We're doing a live tutorial. Okay. Any questions at this point? And I'll take a breath, so you have time. Also, should we do the breaks very much on time, or can we move them back and forth?
If it makes sense to have a break now before we move on, we can do it and finish it.
So we can either do it now, or we can do the optimization, but this is actually a bigger thing. So maybe now is actually a good time for a break. And then we'll do the experimentation in the second half, maybe.
Okay.
Okay, but again, first, any urgent or non-urgent questions so far? Doesn't have to be exactly to that. Anything that crossed your mind that very likely somebody else wonders about as well? Or are you just all looking forward to the break? Yes, please, thank you.
Can you go back to the, I don't know if you have it, well, you don't have it anymore, but you wrote sum 0, but the other ones didn't have sum, oh yeah. It cannot infer from the 0 that you don't need the sum from it?
Yeah, good question. So numerals are overloaded in Lean, because it might be an integer, it might be a natural number, it might be something like a metroid in topological spaces if you like deep in MATLAB. So it uses type class inference to find out what a numeral might be. This is the off-net type class. So it can't at the same time figure out, oh, what is this numeral and which coercion should I insert? So if you have this overloaded thing here, we have to and say this is, well, use the sum inject constructor.
Could you do the other way around? Tell what the 0 is and then it infers the sum?
Yeah, very good. All right, then yes, please.
So use end init to initialize all the variables to the numbers. What if I have x and y now with the different values?
Yes, that's good point. I think I actually had this on this. So let's do this before the break, and we can actually have the break on time. So let's add a function called call it set. It takes the name of the variable as a string, the new value as a value, and of course an environment, and it returns an environment. And then the get function that we get now, well, it's just a function, so we get the y that we're accessing, and if y equals x, then return v, else we just use the old value of y. And now I can, let's say, x divided by y, and let's all of them, give some space here. So we can set x to, let's say, y to 0, and I need to have parentheses here. And now I'm dividing by 0 again. And we could now define nice syntax for adding this thing. That's actually one of the exercises. So I guess it's true that maybe oh well, let's have break, not exercises. Any more questions to help me finish exactly on time? Okay, we can. Yeah, welcome back from the break. I will continue the moment. Just to recap, we've defined a small expression language. I mean, we promised you an imperative var language. We're going a bit slower than possible, but I think it's still the right thing to do. I hope you're not bored by going slower. We gave the expression language semantics, something related of expressions, and now let's go somewhere where we can prove something with about the language. And to do that, I want to first write a little optimizer for our expression language, like a function that takes an expression, builds an expression that's faster in some way, and then we're going to prove that it's semantic preserving. So let's open the optimize function. on, but I don't know. Yes. I should probably keep talking so you can test the microphone. I don't talk and doesn't do the test. I already did my E1 show, so maybe I have to do my E2. Do you get it for the recording or is it just for the room that's missing the voice?
It's both all room and the recording.
Okay, because if it's the room I can speak, but if it's recording then I'm just saying this so we have something to test my voice. So, I should mention that I gave a very complete and thorough Mona tutorial earlier. Do you know? There are minor things that I didn't tell you about monads, and I heard that Nick will in his session in the afternoon. Okay. This is better. So in Nick's session in the afternoon on effect systems, there will be a much more thorough introduction to monads. So if you missed what I didn't quite catch that with this option thing, there will be more of that later. Okay, I want to optimize expressions, and let's maybe look at some expressions that we may want to optimize. Things like 1 plus 2. Oh, wait, where is I have to import the syntax in the operator. Right, so adding two constants in a program, that's kind of pointless. You could just add them and put the finished thing in the context. So let's write that. So let's write a function. Let's call it, we're already in the exparent namespace, so we can just call it optimize. And it goes from expression to expression. And we can pattern match on these things. So if it's a constant, then there's not much to optimize. If it's a variable, then at least for this example, we can't really improve the code. But if it is an operation, let's say like plus, that's simple. And we have two constants as arguments, then surely we can just return the replace it with constant. And if it's anything else, let's just keep it as it is. Very simple optimizer. And let's try to run it. So I take this expression and I optimize it, and we get a constant 3. Okay, that's nice. Nice little functional programming again. Of course, we don't just want to do this with plus, we want to do this with arbitrary operations. So if you have an arbitrary operation, well, we need to evaluate apply the operation. We have a function for that. Remember that that's called e.apply. It takes the binary operation and the two arguments, but then it returns an option. So let's do this only if the operation is defined. So that division by 0 we don't want to optimize away because we don't have an expression we can put there that would be appropriate. So if this is none, we just keep basically this thing. But if we do get a value out, then we can put in the value. And actually, let's use guard messages so we always see what's happening. So this is optimizing it now with plus, and I guess it's also going to optimize this multiplication. Great. Oh, and just to check what we just discussed, if it's not defined, it retains the the original expression. Okay. I said we're writing this optimizer because we want to finally have something to prove. So it's time for our very first theory, given that this is on theorem proving. So the theorem, the command similar like def, it actually has the same syntax. I could have used def because this is type theory, so theorems are just function definitions. But it's still nicer to have a separate keyword for theorem, so we know this is not a theorem. And we want to say that for any expression, it is the case that if I evaluate the expression in some context, that's the same as optimizing the expression and then evaluating it. People are squinting. Good, keep squinting. Tell me why you're squinting, if you find something that's worth squinting at. Extra. So, okay, let's try to do a proof. Since there are so many people here back from ACTA, I'll start by saying that Lean is based on type theory, so proofs in Lean are just terms. And everything we know about writing programs, like pattern matching, recursion, application, all these things, I can use them to construct a proof. But often these kind of proofs are tedious to write manually in all detail of a proof term. So that's why Lean, like Rock and Isabel, and a bit like unlike ACTA, has what's called tactics. And now I hear all the ACTA people in the audience, no, don't come with tactics. They don't like them. But don't be scared of tactic. A tactic is a little meta program that produces a term for you. And I'll actually, let me rephrase this just to show you how unscary tactics are. So I could have given the type of the theorem simply by saying like a function type. If E is an expression, then like give me an expression and I give you a proof of this equality. And we've seen function definitions before. They begin with a lambda, fun E, and then I do something. Sorry is basically a placeholder. So sorry, Lean, I'm not done yet. So this is a term that is the introduction form for the function arrow, or in this case for implication. Well, it's not implication, it's a pi type. And I could maybe try to now write the whole proof as a proof term. If I'm using tactics, let me copy that just to show the similarity. Okay, first of all, I'm using the by keyword to go from term mode to tactic mode. Now I'm tactic mode, which means I can give like line for line, tell Lean how to proceed. And if you look at and this also means now we have these goals here. The goal says, in this hole, in this thing, I have to prove something of the type I gave. For all E, this following equality holds. And one thing I can do as a tactic is to say intro E. And now the goal has changed. The E is now my context, and I have to prove this thing. And this tactic as a tactic, the intro tactic, really doesn't do anything else than just put in a lambda to get the next argument into scope, and then let me continue. So you can think of tactics as little helpers that help you write your proof terms. And I mean, some tactics are big and scary, and they produce huge proof terms, but many tactics are just more convenient, but sometimes more convenient way of just writing the proof term that you would otherwise write. So this is mostly aimed for those who come from a background with like ACTA, where tactics are a bit frowned on. Don't be afraid of tactics. And by the way, we can check that. If I use show term here, it will tell me the term that the tactic produced. And here it says this is actually the same, like it's fun E Theorem, which is actually a thing we don't wrote down here. so you can even see what the tactics are doing. So hopefully this has reduced tactic anxiety a little bit. This is a technical term. Okay, let's continue with our proof here. Okay, what do we next? We want to prove this thing for an arbitrary expression. We know that the function is written by pattern matching, so very likely we want to do pattern matching or the case analysis as well. So I say case is E. This is not a tactic. It produces a match statement. The case is tactic, produces a match statement. And now we have three goals. Case E says, well, E is an expression. There are three constructors inside the expression, so I get three goals. And they look, and we see that where the E was before, we now have the various constructors. So we have one case for const, one case for variables. Oh, we even get our nice express syntax here. And one case for operations. I can now address one of these cases using a bullet. For those who are actually typing along, this is \, period, space. All these fancy Unicode things are \/ something. Oh, I didn't mention that, I should have mentioned it. If you ever see a symbol you don't know how to type, just hover it, which in my case I have to enable it, and it tells you how you can actually type these symbols. So here we see the dot, it's typed using \. Okay. The effect of this tactic combinator is that now we have one goal. It doesn't mean that the other goals have disappeared, they're just slightly out of sight. So we can focus, we are focusing on the one goal. Okay, we have now in the goal that we have to prove that eval of const equals, I guess we can look at this. So here we have an application of optimize in dot notation to the constant, and we know that the optimize on a constant should be a constant. So we tell Lean that it should unfold the function definition and apply this rule. There are multiple ways of doing it. Just to focus on a few things, we'll use a kind of generic rewriting tactic called simp, which applies rewrite rules. And I can tell it to apply the definition of optimize as a rule. And if I now, it even solved it. Why did it solve it? Well, after we optimize the const, it says eval sigma const, and the equality is directly true, and simp can solve it. So simp is a nice tactic to make progress if you have any kind of rewriting to do. And you can pass to simp in square brackets either function names, which means try to unfold the function definition if you find a case that matches, or other theorems like this one that are an equality. Okay, the next goal is the variable case, and it should basically work the same, because we don't optimize variables. Yeah, so this worked. The last case is interesting, more interesting. Let's just see what happens if you optimize. Interesting. So if we can go back to the beginning of the line. If you go on the first character of the tactic, we see the state before. Optimize on one of these option expressions. That's one of these cases, right? It could be either the one we have constant, or it could be not. We don't know yet. It looks like Lean has taken this function definition and turned it into one where, if we know it's an operation, it's not an option case, operation case, then it pattern matches on the argument to find out what's more. And this is what we see here. So after unfolding the optimized definition, it's even worse. Well, not worse, but we told it to unfold the okay, let's do backtrack. We have to told it to unfold optimize. What we see on the right-hand side here now, the green stuff, the thing has changed. That's basically the whole optimized function unfolded. It's the right-hand side of the function, including the match with all these four cases. And the reason it doesn't make more progress is it doesn't know whether it should be in the third or fourth case because we don't know which, like what it should be doing here. Okay, how do we make progress? Whenever we see a match statement in the goal or an if then else statement, the naive thing to do is just to say, okay, do a case split. Give me all the cases that you want to do here. So the tactic for that is called split. Okay, this now splits basically whether the scrutiny of the match statement is what any of these constructors. We get 4 cases again, because we have 4 cases, but some of them are kind of stupid. Like the first one says, well, if the scrutiny, which we know is an operand constructor, happens to be equal to the const constructor. Now this can't be. So probably, let's try contradiction. Yeah, this is a contradiction, we can solve it. What I'm doing right now is kind of the proof exploration mode. I'm just going ahead, trying tactics that kind of make progress. This is not going to be the most elegant proof, and we'll clean up later. But it's a good way of exploring a proof. Maybe you don't even know whether it's right. Maybe there's something missing later. And I'm more or less improvising at the moment, as you might have noticed. Okay, so the first 2 cases are by contradiction, because we know this is not that constructor. Now we make progress. So now we have, and hope you can see this. I'm running into a corner that's less nice than what I've prepared. How did I want to do this before? Oh well, let's just see what happens. I'm going to be honest here. Okay, so we find that we have to prove that the evaluation of the operand constructor with E1 and E2 is equal to this match statement. We know also as an assumption that, the constructor that we matched on with the E1 and E2 has to be equal to the pattern of the case we're in. Like this. This was the match statement that we applied, and this is the pattern that for the case we're in. And for these to be equal, surely these have to be equal, and these have to be equal, and these have to be equal, and so on. So let's just see if we can simplify that. I'm running into a straight corner here. Where did I make the wrong term? Okay, let's try something simpler. This is the corner. Sorry. Let's try it differently. So one complication we had is that we did case analysis on E, and some cases were easy, and then we unfolded the function definition and did another case analysis on the function definition. Now we have 2 case analysis, and we have to kind of line up. Let's try differently. Let's try to sim optimize here before we do the case analysis, and then just split directly. We still get the first 2 goals, but then we don't have to split here again. And let's see if this gives us a nicer goal. Yeah, this is much nicer. Because now we don't have 2 expressions around that we have to compare. We simply know that the E that we had here, by splitting according to the match statement that we have in the function, we have these cases, and they're just right there. And now I can make progress because I know how to evaluate an operation call. So let's try to. Sorry, what did I do? Let's. Okay, we simplify the left-hand side. And then what's on the right-hand side? Oh, there's another match. If there's a match in the goal, let's just split. And then we have the 2 cases. And now we are in the case. This split corresponds to. Yeah, it's a bit unfortunate that we have this wide range because I really need to point at things. Sorry to the far left. I wouldn't want to call you far right. Sorry. So I'm using my perspective here. Sorry, you guys. you're far left from your perspective. You're all, never mind. Okay, so we had this match statement in our goal because we make a proof about this function. And by splitting it, we know that we're in this case. And now we're basically, yeah. I guess, yeah, it's in one case. So this expression here that we have comes from here, and we have to evaluate it, and we know how to evaluate it using simp eval. And if we're lucky, no goals. Yes, we finished this case. Great. There's still more cases missing, which we can tell by the hammer and wrench. So this is now the case where the optimization happened. So we know that apply returns sum, where in this case we return the constant, and the left-hand side of the equality, that was the unoptimized program. There we also use the apply function, and now we just need to know that these two are the same. So let's try to simp with eval. We're almost there. Now we have to prove that. Oh, we removed the one on the right hand side. We have to prove this. It's actually something we have in the context. It's something we by now assume to be true. And we just have to tell sim that it can use things in the context. Let me do one more line, and then we'll discuss it. Because there's still one case missing. I think it's this one where we don't do an optimization. But here the proof is really, okay, we didn't do any optimization. So it's just true by vacancy true. The thing on the left and the right is the same. I can do it with raffle, but let's just use less tactics, so let's say this is set. This can probably go because we didn't have to do it. This is somewhat reasonable proof. For like a proof exploration result. Okay, go ahead now.
But what's that like cross symbol?
Yeah.
It's there is number. Like sometimes there will be a number like 1 x cross 1 is s2. Like,
okay, so
yeah.
the daggers, which is the technical term for these crosses, these are names for things. Names. Again?
We're back on shortly.
Okay. Oh, I see. So the daggers are names of things in the context that I did not give a name to. So remember that here the intro, this is a good way of trying it. Like this E, I introduced with the name E.
Yes.
Like I could have named it something else and it would have a different name. And this means I can refer to it below. Remember that earlier we had a cases E, so I was referring to it. I could have also not given it a name here, and then it's in the context. It still has a name that is like, it happens to be E because, I guess, because I have an E here. But I didn't give it a name when I brought it into context. And Lean embraces the idea of name hygiene here, which means that if you name something, or if you want to refer to something, you have to name it first. And this is the point of this is proof stability. Because often, like if you look at the proof goal here, where do these names come from? The X, the O, the I, I don't know, they're somewhere far away in the definition of the data type, where these are the parameter names of the constructors. Okay. So imagine they weren't daggered here, and I could refer to them here, and I write my proof, and I say I and E and O and all these things, and then somebody refactors a file somewhere far away, changing the names of the parameters in the constructor, and suddenly my proof would break. So therefore, I can't refer to these names unless I give them names locally, and that's what removes the dagger. And for example, this dot is basically just shorthand for something called next, which I look at the next goal. This is slightly long. Oh, we were. This is like equity. Like now you get to see it, and you don't get to see it. So the dot tactic combinator is just a shorthand for next, which focuses on the next goal. And in this form, I can give names to the variables that appear for the first time in this subgoal. And now they are no longer negative. And what related? Yeah, this is tough. Okay. But since I don't need to refer to them here in this proof, I can, yeah, for example, here I could say, I give a name to this thing, and this would allow me to refer to it in the sim call. The sim star says use everything in the context, and also say, dear sim, rewrite with this equation in the context, and now for this I have to give it a name. If I did not give it a name, then let's go back to the dot here. Then it would complain and say, I don't know what HEQ is, even though there's an HEQ dagger in the context.
And that one means that x has repeated once, like x cross 1 in the case h2, there is a 1 after cross.
Oh.
Yeah, that means x has repeated, like in the case of 4.
Yeah, it's shadowed so that you can still distinguish them. Okay. So we've written optimization function, we verified it. Are we happy with our question, please?
Is there something like ESA for instead of these low-level tactics?
Not as, we don't have something that's as separate from the tactic language as here, but you can use have, and you can use suffices, so you can do most of the structure, and we also have card blocks for equational reasoning. For some reason I don't see lean people write proofs in the style of ESA, but you can get close. Simply by forward reasoning and local assumptions. But they will show up in the context.
Just like the question, is it possible to like turn it off the plus feature and the cross feature so that I could use lean to pick up names for me and use it without going next and
so you can set hygiene off. I'm actually not sure if it affects this. No, it doesn't affect this. Wait, hygiene.
There was something in the other
Yeah.
combination. Just start with tactic.
Hygienic, yes. Does this? Oh, yes.
yeah, okay.
Looks like you can turn it off
Okay.
for someone. I guess now it depends on how the tactic works. People don't do it.
Okay.
You should feel bad about it, at least.
Yeah. Okay, are we happy with our optimization function? Or do we have complaints about it? Well, wouldn't it be, so let's see what it does if we do it like this. Oh, it didn't fully optimize it. So if we look at the thing that comes out of here, it's completely unoptimized. But we want to optimize this thing. What did we do wrong? This is a general programming question. Good time for everybody to tune back in. So we have the optimization function. It does constant folding. So it applies, if the operands apply to constants, it replaces it with a constant if it's not division by 0. But still, if I optimize 1 times 2 plus 4, it doesn't do anything. The expression is unoptimized. What did I do wrong in my program?
Just need to call optimize on each of the cyclic.
Thank you. We need to make optimize recursive. So let's do that. If we have, oops, sorry. So E2 and E2 may not necessarily be constants, but maybe after optimizing them, and I'll do it both at the same time basically. If both happen to be constants, then I can do this thing. And in the other case, I'm just returning this thing. Okay, this is a better optimization function, as we can see here, because now it optimizes the thing. So we did the recursive call. But of course now the proof breaks. The question?
Why are you using E1 and E2 in the last case and not the optimized thing you mentioned?
Because I want to write the somewhat suboptimal optimization function first, verify it, and if you do it really well, we can fix that later, and the proof will not break.
I see.
At least it's a goal. So you're absolutely right. If I'm optimizing E1, even if the other one doesn't optimize, I still might want to use the optimized E1 here instead of the original one. So it's not as good as it could be. This was intentional, but good to see that people are paying attention. Okay. So the proof breaks. Simp make no progress, so that's not helpful. Why did it stop making progress? Well, imagine simp would unfold a recursive definition. Simp is a general rewrite tactic. It'll just keep applying all the rewrite rules it has, and if it's recursive, it'll just keep applying it, and it'll just go very deep. We don't want that. Actually, can I? No. But we can unfold optimize. No. With unfold tactic, one step. This is just replacing the optimize call with one level D. And now we have to fix the proof. So we still split. And now we have 3 cases, not 4, so we can delete the last one. Let's do the split first. So in this case, we're matching on whether we have optimization, like whether optimization works or not. So we get the 2 cases here. And in the first case, there's another match because now we're in the. Should maybe show you the code above. Yeah. So now we're looking at this code, and we have to distinguish these 2 cases. So let's split again. And what do we have to do now? Okay, we know that the first one optimized turns to const, the second one optimized turns to const, and we want to apply these over to the evaluation. Let's simp with eval to see what we get at the bottom. All right, let's see what we do now. The right-hand side looks simple. This is just applying the operator to the results that we got by optimizing. The left-hand side is evaluating E1. And how would we make progress? I mean, this is not less about lean, but more about making these proofs. What do we need here? We kind of want to prove that the optimization of the optimized, like the evaluation of the optimized one is the same as the unoptimized one. And we know that the optimized expression is const, so we know that by this theorem that we're trying to prove. Yeah, question?
So I'm kind of some Dutch, so basically what you're trying to do right now is to go real proof by induction. So either we have to activate some sort of inductive invariance, or then find it for us, I don't know, then so magically figure it out.
Right. These are the right keywords. It's a recursive definition. We need to do some kind of inductive induction reasoning. And I want to show 2 ways of doing it. And to cut chase a little bit, remember that I said that proofs in a type theory like lean are just like definitions. This means just like we have recursive definitions, we can have recursive proofs. I can use the theorem I'm defining right now inside the proof. So to do that, I want to be very explicit, forward reasoning, like our Isabel friends want us to do. I want to call optimize OK, and I want to call it on E1, unknown identifier. This is the problem you just described. Let me give a name to E1. So this is part of, I think here it was introduced, so let's say next E1, E2. Now E1 and E2 have names. Why is this not working? Oh, we also have to give sigma as a name. Let's make sigma an explicit argument so that I can. Still doesn't like it. Oh no, this is fine. Okay. So now I've asserted a fact. I used the theorem of defining on E1, and now I know that eval of sigma E1 is eval of sigma E1 optimized. And now if I quinted it, then maybe we can make progress, because if this is equal to this thing, we can use this here. We now also know that E1 optimized is equal to the const, and we know that eval of const is sum, and we know what option sum of byte is. So if you just simplify it all, and I can say, like, use everything in the context here, this looks better. Somehow it could get greatly simplified. Now we have something about eval E2. We have to do that again. We also want to get the fact for E2. And yeah, that's it. So by asserting the facts that we need to tell Lean about our recursive call, the rest is just rewriting. And if you can stare at it with a bit more time and see all the steps that it's doing there.
I have two
Go ahead.
unrelated questions.
Yeah, please.
So the first one being you have defining how being definitionally equal to optimized.
Oh, sorry. This is maybe I should call this H1 and H2. I can give names to these facts, and I could, for example, now say eval with use these while rewriting. The fact is, because I'm using the star, I didn't need to refer to them by name, so I didn't give the name, and it was actually just calling them this. So this is a convention. If you write half without anything, it's called this. The Isabel people will feel it right at home. We steal all the good ideas from Isabel. But yeah, you're right. This is less confusing this way.
So another question.
Yeah.
So maybe I'm being pedantic. I don't
Please
know.
do.
But so earlier you have symbol optimized earlier. So we have some abstract key. We don't know anything about it. So how is it symbol optimized? The symbol optimized is different from unfold optimized because we only have some abstract key. We don't have any more information. Would it be the same? Because you can only do one step reduction. If you have sync.
Oh, but if you let's say if I do many this is what sync would be doing.
Okay.
And now we get to, every recursive call gets unfolded. We don't want to do that. Yeah, but good question. Okay, the other cases should hopefully be simpler because there's no recursive call involved, is there? Let's just try this. No. Oh, I think we can actually move these halves before the split. Maybe that's so. First, introduce these facts, then split. Yeah, this looks good. Oh, we got the check mark. We're done. It's proven. Now, some of you might find this scary that I'm using optimize OK in the proof for optimize OK. Is this OK? Pun intended. And it is because Lean is basically doing a termination check there. We give a whole talk about how to do recursive definitions and theorems in Lean. But just to show you what would go wrong if I were just to say, oh, let's just don't do all of this tedious work. If I can use optimize OK and optimize OK, then just say the proof here is exact, which is basically going back to term mode. Optimize OK, sigma E. Now, this type checks locally in the sense that this is a proof of that statement, but then of course Lean will complain and tell me fail to show termination, and then blah blah blah, all the things it tried. So don't worry, you can refer to theorems in the theorems you're defining, but it's safe. Somebody mentioned induction, and this is actually maybe the more common, using induction is maybe more common than what we did here. So what I did here is I unfolded the definition, pattern matched, like using a case splitting, and then at the right point instantiate the theorem with the right things I want to refer to. It's actually more common to say, oh, this is just by induction on E. Oh, I have to intro E, but undoing and Vim mode does not go together. Okay. Induction E. And now we get, it's a bit like cases, you get a case for each constructor, but in particular in the last case, we also get the information that not only that E became an operation, but also we get the proof that the thing we're trying to prove as assumptions precisely for E1 and E2. Which is even nicer because now I don't have to worry about which E do I instantiate the theorem with. If my function happens to be nicely structurally recursive, then induction gives me precisely the induction hypothesis I need. And okay, this gives me 3 goals, so this should probably, oh, we still need to simplify with optimize. Yes, please do. We need to simp with optimize so that we actually see that case split. We don't have to instantiate the recursive call, and the proof is still the same. It's very simple. And okay, so this is a reasonable proof. There's something like this whole splitting here is still annoying. And we can go one step further in terms of convenience, because, and this is a general advice, if you have a function that you want to prove something about, very often the proof will follow exactly the same structure as the function. If the function is recursive in a certain way, your proof will be recursive or use induction in the same way. If the function has pattern matching in 5 different cases, then your proof will have these 5 different cases. And having to recreate these recursive structure and the pattern matching in every proof is just tedious. Those of you who've done theorem proving will know what I mean, and the other ones will learn it when they try. So another thing we stole from Isabel, well, they still have it, we copied from Isabel, is it's called functional induction. So here I do induction on E, on the expression. It gives me the constructors, that's fine. I can also say, do a functional induction on the call to optimize. And now I get 5 goals. More to work, but actually it's nicer because these 5 goals correspond exactly to the 5 nested cases of the optimize. So basically it does the case split for us, puts us right in the position of what we want to do, and then the goal is probably, let's see, simp with optimize and use everything in the context. So this solves the first goal and second and third. Oh. Do we need to wait? I have to peek. Why does this not work? Oh, it does. Okay, that's just slow. So all the cases can be solved with this, and if all the cases can be solved with the same tactic, we can of course tell Lean just use this tactic on all the cases, and now we got a very short proof of the correctness of optimization. Because and the good thing is now that this is not just short, it's also robust. If you change the optimize function, maybe let me try something. This is not prepared, but you know these 2 cases are basically just catch-all cases. So I could instead say, if it's not an op, just do a catch-all and just return E. The proof still goes through. Completely different number of cases, but the proof is stable. And then let's try what Jan suggested, that we take the optimized functions. Oh, actually I want to show you the effect of this just in case you missed it. What if we have something like this? 1 times 2 plus x. We can't optimize the whole function, but we can optimize the sub-expression. But if we do it like this, we still have there's still the plus and the times in the result. This is because we're throwing away the optimized sub-expression here if we can't completely fold. But of course we want to keep the optimized expression. And now this becomes still the plus, but the other one gets optimized away. And again, I made this change, and the proof stays stable. And this is what you really need for large-scale like proof developments is you have to. I mean, this is an art and a skill to find out how to write proofs and not just work but also are like elegant and stable. But if you can do that, then you can refactor your code and your proofs will hopefully not, like you won't have to reproof everything over and over again. And this is one thing where tactics can actually help a lot compared to just writing out the proof term. Which, if you want to see it, the proof term of these things get huge. So, no, it's actually not too bad. Because the fun induction is hidden besides another term. Okay. All right. Time for questions.
Yes. So the star in the line 22, what does it mean? Like
this star here?
Yeah.
That tells the simplifier that it can use anything in the context.
Okay, so the order is important. First you do optimize, then evaluate.
No.
Then okay.
No, simple is just applying everything it can. It's just you give it a bunch of rewrite rules, meaning theorems with equalities,
Okay.
and if it finds the left-hand side somewhere in the goal, it replaces it with the right-hand side.
So one more question. So I understand sim to perform some steps of reduction.
Mhm.
And at the same time, is it doing some equational rewriting as well?
It's only equation. Well, it's basically equation rewriting.
Okay, so it's like in rock, the sim actually do some reduction, and there is a rewrite tactic for doing the equational rewriting.
I guess it matches the rewrite tactic then. I mean,
Okay.
reduction is a subset of rewriting. You have, like if you have a
Yes, but yeah, so it only does rewriting. So yeah, I mean, I know it's not a well-formed question, but no mind, yeah.
You might also be interested in the desym tactic, which only applies definitionally.
Oh,
building
yeah,
equations.
yeah,
So
exactly.
that is
That was in my mind.
closer to
Yeah.
reduction.
Okay.
Yes.
Yes. Please.
What happens if optimize doesn't terminate? Do we check this for the proof or?
So, interesting. How do I answer that? Maybe a year ago I would have said, well, in Lean, every function that you define has to terminate. Otherwise, Lean will not accept it. I mean, you get the same error that we get otherwise. Well, maybe let's try something like this. So let's do something that's. So here we call optimize now on an argument that's larger than the input. So this will certainly not terminate. Or maybe it will, but Lean doesn't know that. And it'll just tell you it won't. It doesn't terminate. So usually, unless you do something special, and we get to that at the very end maybe, every function definition as well in Lean is going to be terminated. And Lean will just reject it if it doesn't. And only for those terminating functions you can get the function induction tactic. So therefore, if this is terminating, then this function induction principle is also sound.
Is Lean checking that it terminates?
It supports either structural recursion, which is what we're doing here, because it notices that E1 as the argument to the recursive call is a sub-expression of the argument. It also supports well-founded recursion. If you have a relation that you can prove to be well-founded, then you can do recursive functions that follow that. Yes, please.
A very simple question, I guess.
Please, simple question, okay.
We're talking about rewriting, and so in the in the statement of the theorem optimize OK, we've said e.eval is equal to e.optimize.eval. Is there a convention of reading that left to right, and when we rewrite, we always mean rewrite left to right?
Perfect. I could have paid you to ask this question because we just added something to the tutorial last night about that. So, good catch. I find this not the natural way of writing that statement. I would have written it originally to say the semantics of the optimized program is the semantic of the underlying program. And that breaks the proof. It breaks the proof. I wonder if you can spot it if you look at the cases here. Because the simplifier is just always doing left to right rewriting. And
You want to look at the gradient goes after sim?
That's a good idea.
Sure.
Yes, this is good. Because this is something we saw a bit earlier. We need to make progress here. So we need to know what E eval sigma E1 is. And we know something about this, but it's on the right-hand side of the quality. So simp will not rewrite. I admit this is like the tutorial style thing. Like I found that if I turn it around, it just works really nicely for the tutorial. If you're doing this in real life, you might have started this way and the proof will be ugly, or at least have more manual steps and you won't get it as pretty in practice. And maybe you notice this and try the other way and see if it works better. But what if simp would not just rewrite left to right? I mean, of course, something like simp that just applies rewrite rules exhaustively, doing it in both directions would be stupid. It would just rewrite back and forth. But since I guess since half a year or so, it's been released now with the latest release. There's another very amazing automation tactic that has been written by Leo, because I guess he likes set 3, so he wanted to get all the niceness of SMT solving into Lean without hooking into a sound SMT solver. And it's called Grind. And it does many things, but a subset of the things it does is it kind of does rewriting in all directions. It explores the rewriting graph in a way that doesn't blow up quickly. And indeed, if I use the grind tactic here and tell it, please unfold, optimize, and eval, it actually figures out the proof.
And why do you have to remove the star?
Because grind is always using everything in the context anyway. So this tells grind, well, just apply rewrite. I mean, it's congruence closure, if you've heard that term. So it's trying to. I think it's still a good initial model to think of it as rewriting all directions and being smart about how you do that and when you stop. And dealing with equivalence classes of terms to know when you kind of explore it all. And we haven't used it much in this tutorial, but in practice, I think this is going to be a game changer for many applications, because it gets it so much closer to this ideal of, okay, now the proof is trivial because it's just rewriting and arithmetic, and grind will figure that out, even the combination of, okay, it's arithmetic and rewriting, when everything's set up nicely.
And just to get back to that idea of white box automation, should mention there's also a very good diagnostics output of that grind tactic that you can enable, that is also automatically enabled when it fails. That tells you more what is happening inside. But yeah, if you're interested in that tactic, do take a look at our manual. There's a chapter on that. That will be able to tell you much more about that than we can in this tutorial.
Okay, I guess for those who are looking at the recording, Sebastian just pitched the manual on grind because there's much more about it, and probably grind would deserve its own tutorial.
So one quick question, might be a stupid question probably, but let's say we didn't have grind,
Right.
that did not exist.
Like
So
half a year
then we
ago?
have to then we will be forced to write it in the other way, like the eval being left side of equality, like
Not forced.
because
Only forced if you want to use the simplifier to make it as short. I could also,
okay.
let's see, if this is the goal that failed, I guess I need to give names to things. So let's give. Okay. Because what I can do now is I can rewrite with H1 manually, but from right to left.
Okay.
And do with.
Yeah,
So
okay.
you can do this like rewriting in small steps. We only saw the tip of iceberg of how like different ways you can approach this. And of course, everything that simp is doing in one go, we can also do in small steps manually. So I could rewrite with. Actually, maybe let's try to do this. God, I'm blanking on names now. Let's see if I got them right. This is a bit tedious to. Wait, what's the message? Yeah. So if I give names to all the equalities up there, I can I can rewrite with them explicitly. So this is, and now we have eval of const, and I can say rewrite with eval, and now we have rewrite with option bind sum, I guess, maybe. And then rewrite with eval again, and with bind, and now, oh, I guess I also need to name this thing. Rewrite with h, and now we have, yeah, and this sorted. So this is, now I'm just manually doing the rewriting step by step, which is of course maybe what you would be doing as you're exploring the proof.
Okay, so let's say we are in the pre-grind era,
right?
And we don't want to like manually do all such pre-write steps. So if we were in that era, we would be forced to like phrase our things in such a way that left to right rewriting. I mean, we want to use the same tactics that use the left to right rewriting. So we want to like to automate things. We would be forced to like phrase our things in such a way that left to right rewriting makes sense. For example, here, right? I mean, otherwise sim wouldn't just work. Or we could have a different sim where right to left. Right.
Well, what you can also do now, I mean, this is still more manual, but you can tell sim to rewrite this particular thing from right to left.
Okay.
And now, of course, if we, I guess, so like this is now a middle ground. I'm explicitly giving it the theorems to apply, but it asks him to do the steps, and I guess I also need h, and now it's no more goals, and this also works.
Yeah, that was a stupid question.
No, wait. I like your questions. Yeah.
If we gave sim the arrow version of h1 and h2 and then star, would this just cause it to not terminate because it would? Or would it
yes,
something
probably.
useful
Maybe it's removing.
Oh, maybe.
So it's easy to get sim into a loop. Maybe in this case it kind of guesses, okay, you overrode the star, but then you give it an explicit direction for the other one. Yeah. All right. It's until 12:30, right? Okay. So I think. Okay, no more questions. I think I'll change speed now. We went into great detail here, and I think it was really useful to explore these proofs together and everything. Let's make this at least not fail, because we don't want to see error messages here. I'll show you the rest of the development without live coding. So this will be now very fast look at this code something. I hope still many of you get something out of it. It should not stop you from asking questions. I still think that any question is more valuable than what I can just present you prepared. But I'm going to change speed a little bit, just to show you more features. So we've done all these kind of things for expressions now, but we promised you imperative programs. So now we need statements and programs. And the definition of a while, or an imp program, is another inductive data type. And the things we want to put in the program are either skip, the program that does nothing. We want to sequence two programs, so do the first to the second. Now this is an imperative program, so now we want to have assignment. Assignment says, after this statement, the variable with a given name should have the value of the expression here. And now this is again embed the expression language that we had into our language of programs, or our statements. We want to have an if and else, so it takes an expression as a condition and then two sub-programs. And we want to have while, which makes programs interesting. And it has a condition and a body. So this is fairly standard. I think all of you who have done some kind of semantics stuff have seen it. Then, you know, I mentioned Sebastian doing all the things with syntax again, but it's not much different than what we saw before. So this allows us to, the macro rules, yes, and this allows us now to write these programs in nice syntax. This is this is still lean. Like you can still like go here and hover and see expected types and maybe okay. But we've now embedded this imp language into lean as a deep embedding, and we have nice syntax. And some programs we could write, of course, are swapping two variables in the standard way. We can have a minimum calculation that calculates the minimum of x and y. I mean, we don't have parameters and procedures, so we kind of hard-coded the variable names if you want to take the minimum here off, but it's just for experimentation. And we can have recursive or looping functions like programs like factorial that calculate the factorial.
You maybe show the hash print of one of those?
Yeah, good point. So if you print it, we don't get the nice syntax here. Again, this is what you would write if you don't have a nice little syntax for your custom things. People do this if they do. Oh, I see some very sad nodding. So if you don't have something like in lean where you can have nice notation, which you can have in the other inductive theory as well. Maybe not as nice. I don't know. Not as nice as Sebastian. Then you have to write these constructs this way. Oh, then we even have the nice expression here. So, yeah. Yes, please.
If you scroll up, it says deriving something decidable equation. What does that mean? What does that do?
So, lean has type classes like Haskell. So, no, didn't want to do that. Thanks. And deriving means that you ask lean to create the instance for you just by the standard way. So the type classes we instantiate here are wrapper, which allows us to print values nicely, which we actually saw when printing. And decidable equality means we can compare two statements for equality in a proof carrying way. But I'd rather not go into that detail, if that's okay. It doesn't really affect most of the things we're. Let's remove it just to people believe me, and we'll see when we need it. Actually, it's commented out, so I can put it back easily. I don't actually know where we need this. Okay, we have syntax. We need semantics. What is your favorite way of giving semantics to an imperative language with state? Do you have a favorite way? Okay. Oh, no, you need to get your vehicle again. Okay, let's at least make a poll. Who prefers big semantics? Hands up. Nobody. You are bad luck. Who prefers small step semantics? Okay, some more. Who prefers notational semantics? Yeah, my kind of people. We do the big step one that nobody likes. Okay, big step semantics mean we define a relation between a statement that we want to give semantics to, an environment that describes the state of all the variables before running the program, and if the program terminates, an environment that describes the state of the variable after the program. This is a relation between these three things, and the way we define, one way of defining relations in lean is to give them as an inductive predicate. So we use the inductive keyword. It's the same inductive keyword as for data types, but we're not defining data here. We're now defining some logical relation. The difference, maybe I'll make it for questions that if people care about the difference between data and propositions and lean.
I mean, so yeah. I was just asking like the earlier one that was in the set. So you have like the type expression that was in the set. So it's the similar thing with COP, right? I mean,
yeah.
Wrong, right?
So this lived in type.
Oh, this lives in type.
Which is, I guess, what set.
It depends. Like, I mean, in
yeah.
set, it could be some type. I mean, if you are like, so you have the type universes thing going on. So
yeah.
There is also set prop, and you have to like do some sort of things to like make type universes thing. Yeah, there is some sort of thing going on, but
right.
I don't want to go into detail. But the point is that, yeah, okay. So I could just think of it like type prop.
Yeah, but let's not get into detail with that. This is this should remind you of these papers that have like these long horizontal bars and then things above and things below. This is precisely what you're doing here. So it's just that the lines are shorter and vertical. And actually they're not between the things. So the semantic of a skip statement is that whatever the statement was before is the statement after, and it terminates. The semantics of a sequence of two statements, and now you see the tilde because these are variables in Lean, these are not concrete programs, S1 and S2, which wouldn't be syntactically correct anyway, is that, well, if the first one goes from sigma to sigma prime, and the second one goes from sigma prime to sigma double prime, then the composition, the sequencing of the two programs goes from sigma to sigma double prime. And if you had this as like, just to make this, wasn't there a pen here a moment ago? Oh, it was there. So just to help you read this, this should remind you of essentially something like statement 1, statement 2 in sigma goes to sigma prime. I'm making up syntax because that's what PL people do most of the time when they write papers. Everybody has their own ones. So this goes to... So if you've seen papers like this, then you hopefully recognize this kind of style of writing an inductive relation, and this is the syntax we get in Lean. And it happens to be exactly the same syntax as for data types, because proofs are programs and propositions are types. Okay, I just digress. If you want to assign a value, then the statement, like the state changes from sigma to sigma, where x is v, where v is the relation of the expression, if it exists. If the eval function returns none, then this will not apply. And similar rules for true, for if and while. They actually are kind of similar. Let's only look at while. If is similar. For while they have two rules. One, if the condition evaluates to 0, then the state does not change. And if the condition evaluates to something that's not 0, then we evaluate the body and run the while loop again in the new state. So this would be the figure with all the horizontal lines. And now we have this in here, now we can do proofs with it. I will just show you some of the proofs without going into too much detail about the actual tactic proofs. So we can, for example, show that if we somehow know that the semantics of a skip program relates sigma and sigma prime, then the two must be equal. One direction is just the constructor that we had, like the big step with skip. The other one follows by what's called rule inversion. Because there's only one rule that matches this thing, and it happens to have with sigma and sigma prime, and we can use cases for it. We can prove that after running swap on some sigma, then there exists a sigma prime, which just this part already, just the first existential here, shows that swap terminates. There is a resulting state, but we also know that afterwards the value of x in this state happens to be the value of y in the previous state, and the other way around. I saw a question.
So again, a type theoretic question. So
yeah.
You have like sigma and sigma prime, that's functions, and you are saying functions are equal. So do we have like functional extensionality within the type theory, or
yes, it's an axiom, but it's very deep in the library, so it's not technically strictly. Oh wait, no, does it follow from the quotient? But from the axiom about quotients, right? Yeah. So it's technically not axiom. There's an axiom about quotients, and that implies functional extensionality. But for practical purposes, it's just built in. And most Lean users don't even want to think about functions being something else than just their extensional behavior. Okay, is there anything? So we can prove this, and okay, this is kind of cute. I'll briefly show it. So this is the step-by-step proof exploration tactic proof. I unfold swap. Okay, I get this big statement. I go into the existential. Oh, and this shows something new. Maybe that's worth pointing out. So before, we have to prove an existential statement. Usually, when you prove an existential statement, you have to give evidence for the thing that the existential should hold. But I can say, oh, I will do this later. So I'm applying the exist intro rule without giving the evidence, and now I have what's called a meta variable. That this is question mark W, and this is something that it's a whole. It's something that I haven't written yet, but maybe I will write later, or maybe Lean will figure it out later, and I can make progress in my proof. And then this constructor is just the conjunction here for the AND. And now I have to prove that what big step is doing, and this looks very much like, maybe we can squint and see the sequence constructors here. So we can apply the rule for sequencing big step, and we use apply there. And now we get two goals, one for the left and one for the right. The left one is still it's not an assignment. We apply that rule, we get some goal, and maybe you remember the rule, maybe you don't. If you apply, for example, this assign rule, like this constructor here, then we have a goal about eval, and this is what we have to prove now. And this will actually instantiate this meta variable that we see here. So if we go back to our proof, where is it? Yeah, we just say, okay, just do the computation, and then we instantiate this meta variable here. This is one variable, it just has a long name, to whatever x was in sigma. And we repeat the whole thing. We basically walk through the program, applying our rules, very straightforward. Whatever we see, we just do the obvious next thing. We do we evaluate our expressions with the eval function we wrote before, and then and this not only proves that it terminates, but also instantiates the meta variable of the state afterwards. Because now we get like this whole expression set. That's the new state, and then you have set of get, and this can be solved with a simplifier. Because there are some rewrite rules about set and get that I didn't show you, but we had to add for our environment type, of course. The cute thing of it, this wasn't very helpful. This is showing like this is like the way you do these proofs, but without going into much detail. The cute thing I want to show is that we can do the same proof with this proof, and this is because of all this like type theory fanciness where applying a theorem and applying a constructor and applying a function, like this is all similar. And all the things I did up there, including REFL, which is proving the equality of two equal things, these are all constructors of some data type. So this is not a common thing. But in this particular case, I can just say, just apply constructor all over again. Always apply the one constructor of the type that you're looking at that matches, and you can do the whole proof. This is more cute than helpful. Okay, I wanted to go faster to make sure, well, not faster, I want to go at a higher level of abstraction. So let's look at what else we can do. In the files you find also an optimization function and a proof that this optimization preserves the semantics. So the optimization here is just applying some common program transformations like removing skips, removing if then else if the if has a constant condition, or if the two goals are equal. Oh, this is where we need the deciding inequality. Somebody was asking about the optimize function for if then else looks at the then branch and the else branch, and if they are the same, we just want to remove the whole if then else. And this requires me to compare these programs. So I guess if I run this, or maybe it breaks in the proof. Oh yeah, failed to synthesize decidable on programs. So let's, but I want to, where's our big step basic here? Okay. So if you reload, then it should not work again. And then as before for expressions, we can optimize we can verify the optimization function. I think it's actually in here, and prove that if the original program had some meaning in the semantics, then the optimized program has the same meaning. This goes by induction on the derivation of the. I mean, this is a sentence you hear too often, right? The proof is by induction on the derivation of the predicate, and this is like you can say this like for every second proof in PL, and people will say things. Okay. Yeah, I want to get to the show-off thing, and then we still hopefully have a few more minutes for more questions. Another thing we want to do with programs is to run them. And here's a let me remove this thing. Here's a recursive definition, a recursive function that takes an initial environment, a statement, and calculates the resulting environment. And this should be an executable function that we can run to test things. And it does rather obvious things. So if we skip, then it's some value. If we have a sequence, we run the first, then we run the second. This using, again, the do notation for option, so that if evaluation fails, we propagate the failure. Same with evaluating expressions. So this is a plain interpreter for the while language. And we can now run our code. So here we use the factorial program that we had before. We run it in an initial environment with everything set to 0, but n set to 10. And then the resulting environment, well, get exclamation mark gets the value out of an option, because we know it returns some environment. And then we get the value of the variable out, and we find that this is the number that comes out. So this is an executable interpreter for our while language, and we can even we could compile this now to a proper native machine code program that we can run. As we said, it's a programming language lean, so I can write a main function and do a I/O and run this interpreter that way. There's something peculiar about this function in that it is interpreting a while language. It has a while loop. So clearly there could be non-termination. I could pass the function, the program while true to the interpreter. And let's do it this way. Yeah, we have time for that. So the maybe more natural way of doing that in Lean would be to say, oh, this function is partial. Partial in the sense that it may not terminate. And this just tells Lean, oh, don't even bother termination checking. This is not something I care about termination. I just want to run this code as programs. And if you're using Lean as a normal programming language, as like a replacement for Haskell or Camel, you usually don't care about termination checking. I mean, it's nice to know that things are terminating if Lean can figure it out, but if Lean is not smart enough to know that your function is terminating, or if you know the function isn't terminating on all input, but you still want to run it, that's fine, you can do it. And this is what makes Lean a practical programming language. And I can make this partial, I can compile it, I can run it. What I can't do with a partial recursive function is prove something about it. So here I'm trying to prove that whatever state sigma we have, if I run the skip program, that we get the same state out. And I could try simplifying it, and it'll just tell I can't do it. That's because you can't really have. Oh, how do I put it to not paint myself into a corner later? Okay, maybe let's put it this way. Yeah, like completely unrestricted termination recursion would break the soundness of the system. So we really don't want arbitrary recursion like we have in Haskell or Camel in Lean, because it would make Lean pointless as a theory prover. Yes?
I mean, if you do check run, I mean, what's the type of run? I mean, if we try to do the.
So if you check run, it has the type you gave it. So the effect of partial is, to be precise, it adds to the logic something of that type, but it doesn't have any more information. Like the logic doesn't know anything about it. It's opaque. And this is okay in this case because the type is inhabited. So this doesn't break soundness to add just to tell the there exists a function called run. It has this type, and I'm not telling you anything about it because the existence of something of this type is fine. Option is inhabited. If I were to use partial def with something like clearly bad, let's say partial def bad, let's say I take an arbitrary proposition P and I would want to return a proof of this P just by using bad itself. It tells me can't compile a partial definition because the type is not non-empty.
In the other case, I could see that it is inhabited,
Mm-hmm.
and in some sense, I can intuitively think that it wouldn't break logic. Like, in some sense, I could think that way. Yeah. So I was just wondering, like, how can a partial function have type, but I can see that it is inhabited, like that type in some sense.
Yeah.
Yeah, I think that works well.
And from the point of view of the kernel, this is not a partial function. This is a total function it doesn't know anything about, and could logically just always return none. Which means we can't prove anything about it, anything useful. It just means it only exists in the world of executing programs. But however, this is an interesting special case. In particular, this is a function in the option monad that is written just using the monadic operations, like option byte. And there's a theory of recursive definitions that are not terminating, but they are still. It's hard to explain this. You can still, well, the defining equation for this function, run sigma s equals to this thing with a recursive call, is still consistent with the logic. So for this particular function and the class of similar functions, we can actually tell Lean, or I can ask Lean to say, it's not a terminating function, but the equation it's used to define it is still doesn't break soundness. And there's a class of functions where this is the case. Because this is somewhat weird, this is opt-in, but I can say it's a partial fixed point, and fixed point may remind you of domain theory, which is the underlying theory there. I will take that into the break, that like how the construction works. But now we do have this function also from the point of the Lean kernel, including its defining equation as a rewrite rule. And this means I can actually, although it's not a total function, I can prove things about it. I can prove that for this concrete input, it's I can prove that it's partially correct, saying that if run terminates, which means it's returning some value, it's not none, then I can, for example, in this case, prove that it corresponds to the big set semantics. And that works using some partial correctness theory that Lean has provided to me. It's a bit more tedious, there's less convenience around these things at the moment, but I can do it, too bad. I can also do it the other way, and this is very nice short proof, if the big set semantic, if according to the big set semantics we have the semantics for S, then it matches the one on, then we also get that when we run the run interpreter. And this works by, what is that again? The proof is by induction on the derivation of the predicate, which is induction H. Remember, H is the big step predicate. So now we get all the cases from the big step semantics, and in all of them, like in most of them, simp can just do it. In while true and while false, we somehow have to help simp, otherwise, like to only unfold one step and then sim can do it. So the proof is still somewhat short. And so we were able to define a possibly non-terminating, no, for some inputs non-terminating interpreter, and still proved it sound and correct. Totally correct with regard to our big step semantics, using this partial fixed point machinery. When we gave this tutorial a year ago, we didn't have this yet. So there we showed you how to use fuel. Fuel is the idea that you add an extra parameter to the function, which is a natural number. You just decrease it in every recursive call. And if it's 0, you just do something else. And then you can do a similar proof. But no, you don't have to do this manually anymore. Okay, and now for the final finale that I want to show. So here is a programming our imp language that's it's copied from Hacker's Delight. It's a book on like little bit fiddly tricks for how to implement some operation efficiently using very few operations. Remember that we're using 32-bit numbers here? So these sequence operations calculate the pop count. Pop count is the number of set bits in the thing. And it's supposedly very fast compared to just counting like a loop over the bits of the thing. And we can define this as our int statement in our language using nice syntax. So it's probably easy to eyeball it and compare it with the thing in the book. We can also give a specification. It's a normal recursive functional program for pop count where we count down from 32 as a recursive function, and then we check whether the bit is set and we shift the other bits to the right. This is a reasonable function implementation of pop count, counting the number of ones in a 32-bit number. We can write a test that, given a uint32, that the pop count, if you run it using our interpreter, remember that's the partial function we just wrote, or just saw, then that returns something, and it's the same as you would get out from the specification. I call this test because we can test it. We can just run it and we get true for 0 and 1 and 55 and others. But because, it looks like a function returns a bool, but we can actually just treat it as a theorem, and we can actually prove it. Let me load this. And this is, oh, something's broken. In statement big step. Let me just let's see if this works after reverting everything that we may have changed. Okay, good. So we use simp to unfold everything, like all the functions that we have, test popcorn spec, the unfold the run function, evaluation function, and we get a very large thing we have to prove. This is now the specification of, I guess the left-hand side is the unfolding of the imp program according to the Hacker's Delight book. The right-hand side is the counting the bits bitwise for all 32 bits. Now, we don't want to do this proof now manually, but this is where you benefit from the fact that you have tactics that do more than just a simple thing. There's a tactic for bit blasting, which is exactly tailored to this kind of task, where everything is a bit vector, like a finite bit number. You have the operations, and it's calling out an external tool to check it, but it's reconstructing the proof from the external tool, like it's calling out to a set solver. And it gets a certificate from the set solver, replace the certificate within Lean, so this is fully trusted. You don't have to trust the set solver to be correct. You just use it to find the proof, and then it's replaying the proof, and that solves that goal. So this shows how you can nicely integrate very powerful specific tools into Lean, and then even make it part of your regular language of tactics. Yes, please.
What does the certificate from the set solver look like?
Good question. I don't know. It's an LRED file. Does it say you something?
Is this a set solver or an SFT solver?
Set solver. It's Canonical, I think, that we're shipping. I wonder if we we can try to trace it, but probably I think there's a, okay, reflected logical expression. How? No, it doesn't. There might be a way of seeing it. I don't know, but there's even a way of storing it in file and importing it. If it's really large and takes like minutes or longer for the set solver to solve it, you can store it, commit it to your repository, and then checking the proof again if you don't change the input means you don't have to run the set solver again. But I don't know how to do that. All right. Yeah, at the end I sped up. I hope that's fine. I hope it was worth doing it slowly in the beginning. I hope you have many questions now. You can ask either now or later over lunch. We're here until tonight, but we're leaving tomorrow. So don't wait with questions for us until tomorrow, because then you have to write us. If you do that, that's fine as well. Oh, yeah, maybe final slide, yeah. So if you're hooked on Lean, or if your professor tells you have to learn Lean even though you're not hooked, there are some good books to learn about using it, either from a theorem proving angle or from a programming language angle. Both are well doing. Don't try to do it on your own. If you don't have colleagues next to you that know Lean, don't be shy, go on Zulip. It's like a chat program, it's like Slack or Bettermost. There's a channel for new members where it's okay to ask questions that feel like it's a beginner question, and people are very helpful. You will have a hard time, I mean, some people do, but most people have a hard time learning Lean if you don't have somebody to ask to. So please do. And then most importantly, have fun. Thank you. And maybe two or three final questions.
So maybe I'll ask a pilot question.
Yeah.
So let's say you are someone, like I'm sure there's so many of us in the group who's tried a theorem program before, your profession in say rock. Give me good reasons to switch to Lean.
So, I mean, yeah, maybe you have, what's your thing?
Maybe just to make it very specific, you can say a few things in this tutorial that do not exist as such in other systems. I mean, yeah, starting from the top, the syntactic extensibility usually goes further than in other systems. Like this entire macro system, also with guaranteed hygiene that exists well, in languages like Racket, but not in other theorem provers as such. Specific tactics that we've shown, grind, this very new tactic, does not exist as such in any other system, I believe, not to a comparable degree.
Yeah, I guess Sledgehammer is comparable, and I expect what the user experience will be.
Yes.
Isabel. But probably the deep integration into Lean will make a difference in some cases.
Yeah, it is also very high level of automation, but in the end it's a quite different approach.
Yeah, that's true. One argument that I heard from people switching from Rock to Lean is the fact that in Lean the meta language is Lean itself. So let's say you're writing a tactic. If you do that in Rock, you have to use OCaml. If you use Isabel, you have to learn SML. In Lean, you learn Lean. And you not only have to deal with only one language, it also means that the whole environment, the IDE, the hovers, the click to definition things, they just work across the object and the meta language. So this was one argument I've heard from people who would switch and were very happy about it.
So is it just a matter of time that the programming languages community, I mean, you still see burst proofs in Rock? Or is it just because it's
So,
new?
I mean, if you have an application that requires a specific library, like Iris is a classical example. Iris is a huge undertaking in Rock for separation logic, and if you need that particular library, and it's not in Lean there yet, then that's a good reason to stay with Rock until maybe there's a library in Lean. I'm not going to make predictions about whether any of these systems will be the only one. I just hope we're have healthy competition rather than extinction. And I have a warm spot in my heart for Isabel. I use Isabel a lot, and there are things about it that I still think are very nice. So, yeah.
Well, to get students started, Rock has very good support with things like the software foundations tutorial, it's interactive. Is there an equivalent in Lean yet? Is there
So the best thing to get people hooked seems to be the natural number game, which is an online tutorial about basic math. It's very basic, but it's a good way to get started. We don't have something like software foundation, like specific for PL in that size yet. I expect this will be a matter of time until somebody writes it. People have made attempts. Yeah. But otherwise, I think these two books are also a good starting point. More questions that I can answer on record, please. Yes, please.
I was wondering, I've seen this for other theorem approvals. Is there like a big repository of known mathematics that have already been sort of put through the system that we can look at?
This is actually maybe one of the selling points of Lean is that we have MATLAB 4. It is a big repository of mathematics, and it's big. I mean, it's like 2 million lines of code these days.
They're getting close to that, yeah.
So it's huge. Maybe, I don't know, number of commits? Yeah, 22,000 commits.
I guess the follow-up question is then, how does it compare to the other ventures of redoing the math in
I don't know much about how the ROC community does the mathematical thing. I know that Isabel has the archive of home proofs, which is also impressive in size. My understanding is that it's a bit more compartmentalized. So in the archive of home proof, it's separate developments, a bit of like a journal in the idea that you submit something, and MATLAB is more like a monorepo where people just go through the whole thing and refactor something in a way that makes it more consistent. So maybe I would, without knowing the details too much, I want to say bad things about other systems. I would assume that MATLAB is a bit more coherent and maybe a bit more agile in that way, rather than the archive of formal proofs. But the amazing thing is that they keep it running. Like you submit the thing 20 years ago, and even if they change Isabel, they're updating this thing. Thanks for that. I have some stuff there that I haven't touched in years and it's still running, that's great. But the MATLAB approach has benefits for like cross-cutting changes and being more consistent in style across the whole thing, maybe. And it has huge momentum. And it has lots of undergrad math, but it also has reached the edge of research mathematics in some places.
Is there lead time in development?
No.
Given that you've got this huge library for Lean 4.
So it already existed for Lean 3, and it was a huge undertaking to port it to Lean 4. I think nobody wants to go through it again. So
Lean 4 is the final.
As far as I know, it's.
Yeah.
I mean, software is never done, but hopefully it'll just be Lean 4 being improved all over the place, and not a rewrite. But then you have all these young people in this room who maybe in 10 years think, okay, this old rubbish Lean 4 has been around for longer than I can remember. Let's redo it from scratch, and then you do it from scratch and do it better. But until then, I hope Lean 4 will be good enough for all our purposes. All right, then lunch.